have said that for any group, the structure constants can be found from the defining representation. I did not mean that they belong to the defining representation. So I want to clarify that. They can be found in every case. Then there was another thing. We were discussing this question. Supposing that you have found a solution, irreducible or any solution to the commutation relations of the rotation group, when can you be sure that upon integration they give you a representation of the Lorentz group, rotation group? And I said that this condition must be obeyed. It's a kind of global condition. I left it as something for you to easily show for yourself that the condition I wrote down is really the same as this condition. Okay, really, I leave it to you to convince yourself that it's true. And what does this condition say? It says, if you look in this space of axis angle parameters and you look at the surface of the sphere of unit pi, this thing says, please represent an element on the surface in the same way as you represent the diagonally opposite point, antipodal point. Do not distinguish between them. And so this is the global condition. And the commutation relations do not have this information in them. So it has to be explicitly imposed. And so if commutation relations are obeyed and this global condition is obeyed, then you know that starting from the generators by a process of exponentiation, you will get a representation of really a representation of the rotation group. All right. So we were discussing from this point of view, starting from the commutation relations, what the unitary irreducible representations look like. And I had made the statement that for every integer L, there is one irreducible representation of dimension 2L plus 1, and in that representation one can introduce an orthonormal basis made up of eigenvectors of one of the three generators. All this we have borrowed from the quantum theory of angular momentum. And what is the range of this magnetic quantum number? Naturally, it takes 2L plus 1 distinct values because that's the dimension of the representation. What it says, what it means is the following. If you start with the irreducible representation number L of SO3, and if you restrict yourself to two-dimensional rotations about the z-axis. So it is a subgroup SO2 with the axis being E3. The representation of SO3, which is irreducible at that level, when it is restricted, it will in general become reducible. And the result of this reduction is that each one-dimensional representation of the subgroup SO2 appears for M taking this set of values. All right? So that's the meaning of the statement that the spectrum of the generator J3 is L, L minus 1 up to minus L. In the language of representations of the original group restricted to the subgroup, this is the statement that can be made. Now we can use this very well right now, because we also saw that in every class of equivalent elements in the group SO3, we can pick up an element, a representative element. I forget now the notation I have used. Yeah. I can find in every class in SO3 a representative element belonging to the subgroup of rotations around the z-axis. So if this is so, and if this is the way in which the reduction happens when you restrict to the subgroup, it follows that we can immediately calculate the character of the unitary irreducible representation L of the group SO3. Let us denote it by chi superscript L argument alpha. This alpha is just the angle of rotation. All right? Yes. Which part? So these are the various equivalence classes in SO3, and here the range of alpha is 0 to up to pi. The class script C of alpha consists of all rotations by amount alpha about all possible axes as directions. And what we saw yesterday is that in every class of this kind in SO3, you can find a representative element which is a rotation about the z-axis just by that amount alpha. So since we know how the representation breaks up under restriction to the subgroup, and we know that every class has an element in the subgroup, we can put these two statements together and we are able to calculate the character of the various irreducible representations of SO3. You limit yourself to a subgroup element, then the thing will be diagonal. J3 is diagonal in this basis, and this is the character of the irreducible representations of SO3. And this can, well, according to my notations, there's a minus sign here, doesn't matter, or maybe it does matter for consistency. And this is the result of summing this geometric series. So these are the characters of the irreducible representations of SO3. Now we will exploit it again in a moment. So first you see that this character is a real function. This is consistent with the statement we have made that every irreducible representation of SO3, and therefore also every representation, can be brought to real form. The reality of the character is not a guarantee that you can express every irreducible representation in real form. It is consistent with that. All right? I have not gone into this part in too much detail, but let us take it at that. That the reality of chi alpha for every L is consistent with the statement that every irreducible representation can be made completely real by suitable choice of orthonormal basis. Now, we have seen last time the way in which we can define a scalar product between any two square integrable functions on the group SO3. We have given expressions for this in all the coordinate systems, in the axis angle description, in the Euler parameter description, in Euler angle description, all of them. Now, supposing that our function is a class function. What does it mean? It is a function which is actually dependent only on the angle of rotation, not on the axis of rotation. So that would be a class function. So by limiting ourselves in this scalar product to class functions, you will find, if you look at the equation which gives the expression for the scalar product, there is an integration over a certain domain in alpha space involving the volume element d3 alpha and so on. So obviously the integration over directions is trivial, it just gives a solid angle, only a radial integral in alpha space is left. and let me just write the result. Among class functions, the scalar product comes out to be exactly what I am writing now. So, among class functions, functions on the group which are constant over each equivalence class, among them you have a scalar product definition. So, this comes from the expression for invariant integration which I have given yesterday in the axis angle description. We now put this result and this expression for the characters together, and I want you to convince yourself the following statements can be made. This is my equation 48. That one also I have given the number. What I would like you to show for yourselves is the following, that if you take characters of the irreducible representations, they are class functions, calculate their inner products according to this definition. By explicit calculation, you can check that they are mutually orthogonal, which is what we expected, we know should be true from the general theory. We had proved this for finite groups in the first part of this previous section of this course, and here for the group SO3 it is something you can explicitly check. You can also convince yourself by some means or the other that any class function can be expanded as a convergent infinite series in terms of the irreducible characters, and using this mutual orthonormality property of the characters, you can write down a formula for the expansion coefficients, and you can be sure that, what is this called? What equality is it called? Somebody's equality. Whose equality? Students. What's the name of this last statement? Isn't it Parseval's equality or something like that? Parseval's equality. So, these are things, it may look a little strange that for square integrable functions over the domain 0 to pi with this much as the weight factor, these characters form a complete orthonormal set. Conveniently, the sine half alpha in the denominator cancels the sine squared half alpha in the weight function in this scalar product definition. So, this is very easy to check, and the nice thing is that essentially we are saying if you cancel the sine squared half alpha there with the sine half alphas in the denominator, we are saying that for functions of a variable alpha in the range 0 to pi with measure just d alpha, this set of functions sine L plus 1/2 alpha for all integer L including 0 is an orthonormal complete set. Okay? So, this is something which I would like you to check for yourself. Connect it up with what you know about Fourier series. See how you can arrive at this result starting from Fourier series formulae. So, this was the expected completeness and orthonormality relations for the characters of irreducible rotation group representations. Now, we will go into this matter in a little more detail. We will look at the representation matrices themselves. So, in the UIR number L, we have a basis, orthonormal basis in the representation space. Now we know that in the axis angle description, the operators representing different group elements are single exponentials of the generators of this form. So the rotation alpha, vector alpha, would be represented by the matrix which I am writing down here, a 2L plus 1 dimensional unitary matrix. And so these would be called the D matrices for the Lth irreducible representation. But you can see that this axis angle description, which is very convenient for general theoretical analysis for variety of things which I have illustrated.
Sorry.
Yes, yes.
We also have a completeness relation with the character things, chi L alpha prime, chi L alpha, sum over all L delta alpha.
Correct, and that is exactly what you will get from that Parseval inequality by peeling off the f's. Remember, the last thing I wrote was inner product of f with itself is sum of the mod squared of the expansion coefficients, and we have a formula for the expansion coefficients. So you put those two together, you will get exactly that is the completeness statement. But I did not write it in that way, but it is there. So you can see that the sense in which axis angle variables or canonical coordinates of the first kind, as they are called in this instance, are not very convenient when you wish to describe the matrices explicitly in this basis for finite rotations. And it is in this sense that the Euler angle description becomes more convenient. And so let us see how that happens. In the Euler angle description, each finite element of the rotation group is written as a product of three exponentials, and each exponential is somewhat simple. So the complication is in the fact that there are three operator factors, and of course they don't commute with each other, but you can simplify this expression. What is the theta dependence of this matrix element? Anybody tell me? This is equal to e to the minus I m prime theta. What is the phi dependence?
Plus, the first term is plus. E power plus I m by theta.
Why? Why do you think it should be plus? Suppose you were to take a power series expansion of this exponential, it will be 1 minus I theta j3, etc., j3 squared, and so on. J3 is a Hermitian operator. When it sees an eigenvector of itself on the left, wherever there is J3, it will become m prime. No change of sign. And then you soup it up into the exponential again. Okay? So what you said is well motivated. It means that you anticipated there is something to be careful about here, and that is correct. And when you do it carefully, you do not have any plus sign, you get a minus sign. And what is the phi dependence? And then what do you have? L m prime e to the I or minus I. By our notation or convention, it is minus I. All right. Now, I had asked you, yes, so you can see that the convenience of this Euler angle thing is that the D matrices, which are actually functions of three independent real parameters on the group, they simplify drastically The dependence on the two Euler angles at the left and right hand end, that part is trivial, it can be pulled out. The only non-trivial part of the D function, D matrices, is a function dependent on one of the three Euler angles, namely psi. And this is called the little d function. Little d function. And we already know immediately some properties about the little d function. Namely, yesterday we made some statements. In the standard basis, I gave you the matrix elements of J1, J2 and J3. What kind of matrix is J1? You told me yesterday. Real symmetric. What kind of matrix is J2? Antisymmetric. Therefore, what can you say about the little d matrix? What kind of matrix is it? Does it have complex matrix elements? Can it be complex? It's completely real. Moreover, as a matrix, it is real orthogonal. Why? Because J2 is antisymmetric. So it's the exponential of a real antisymmetric matrix, therefore it is real orthogonal. So this is a simple, nice properties of the little d functions. And now comes the completeness. So we are going beyond the completeness of characters for class functions, and I'm just going to describe to you the way in which any function on the group SO3, any square integrable function on SO3 can be uniquely expanded in terms of the set of all matrix elements of all irreducible representations. So I just write down the things, the properties. Take any irreducible representation L, any row, any column in that representation. Take any other representation L prime, any row, any column in that representation. Put a star on one of them, integrate over the group with the invariant normalized volume element, which I have written down yesterday in 3 different forms. This thing will be 0 if the two representations are not equivalent, if they are not the same. Even if they are the same, it will vanish if the rows are not chosen to be the same, columns, and it will vanish whichever. If either the rows do not match or the columns do not match, you get 0. They are mutually orthogonal. When everything matches, it is not normalized to unity, the D functions are normalized to 1 over the dimension. So this is the orthonormality property of the representation matrices. You have to include all the irreducible representations of the group. That means L and L prime must go all the way from 0, 1, 2, 3 up to infinity. For each choice of L prime and L, the magnetic quantum numbers must go over their full range from minus L to plus L, minus L prime to plus L prime. And now the completeness. So this is only orthonormality. The completeness is the statement if you took any square integrable function on the rotation group, that means what? In the quantum mechanical language, any wave function for a rigid body with any one point fixed, it can be uniquely expanded as a series, and I don't indicate the ranges of these summation discrete variables, you know what they are. any square integrable function on the rotation group can be expanded with a unique set of expansion coefficients in terms of the matrix elements of the representations of all irreducible representations, L equal to 0 up to infinity and m's appropriately. And how do you get this expansion coefficient? You just use this orthonormality condition. And let me emphasize the fact that this expansion can be written down is not guaranteed by the orthogonality property. That is an additional, very non-trivial statement, that these functions, the d's, are not only mutually orthogonal, there are enough of them to be able to expand any f of a. And the last statement is that the norm squared of f, in the sense of the norm I have, inner product I have given yesterday, is reproduced by the sum of the squares of the expansion coefficients. So this is the orthonormality part, this is the completeness part. And I want to stress again that the completeness is an independent, highly non-trivial property of the d functions. It is certainly not contained in this statement. I want you to be very sure about, very clear about this. And here just an minor and small story. When you do elementary quantum mechanics, you do the problem of the wave functions of the harmonic oscillator, hydrogen atom, find all the bound state wave functions and so on. It is relatively easy to prove that eigenfunctions for different energy are mutually orthogonal. Whether it's a hydrogen atom or harmonic oscillator, the analog of this kind of statement is relatively easy. You just have to play around with differential equations, use properties, known properties of special functions and so on. The proof that the set of all eigenfunctions of the Hamiltonian for the harmonic oscillator are actually a complete set, it is not trivial. But it can be done. It's not very difficult, but it can be done. For the hydrogen atom, suppose you take all the solutions of the bound states of the hydrogen atom, all the Schrodinger wave functions for all principal quantum numbers L and M and so on, will they form a complete set for the set of all three-dimensional wave functions? Yes or no? For the hydrogen atom. Physically, what do you expect? This is not connected with my notes, I am just asking you extempore. Do you think that the set of all bound state wave functions in the hydrogen atom form a complete set? That every Schrodinger wave function of the electron in three-dimensional space could be expanded in terms of them? If you don't know, just take a guess. You can either right or wrong. Huh? Should be complete. Anybody else? But we are talking of the hydrogen atom. So I have specified the system. It is not a free particle system, but you are answering in the right direction. So I appreciate there is a point in what you are saying. It will lead to the answer. What do you think is the answer? Exactly. So when you solve the Schrodinger equation for the hydrogen atom, it's not enough to just look at bound state wave functions to get a complete set. Bound state wave functions, they are the ones which vanish at infinity exponentially fast and so on. They are mutually orthogonal. That part you can quite easily verify. They by themselves are not a complete set. You have to add the scattering state solutions, positive energy solutions, which at infinity are like diverging plane waves or spherical waves, one thing or the other. And then you have to convince yourself that the combined set of solutions, this bound state solutions plus the scattering state solution, when you put them all together, you have a complete set. Now, in most textbooks of quantum mechanics that I am familiar with in the early years when we were students, the completeness was never attempt was made. I don't know, maybe it was mentioned, but even that I am not very sure. So sometime in 1978 or 79, I wrote a brief paper in American Journal of Physics proving the completeness of the complete set of solutions for the hydrogen atom problem. And they accepted it. The referee said, it looks very reasonable, but I also couldn't find any available textbook where it is actually proved. So I don't have the reference, but you can have a look at it. So it is just to say that the proof of completeness is a non-trivial problem. And for all compact continuous groups, there is a general theorem called the Peter-Weyl theorem, which proves that this kind of thing, that the set of all D matrix elements of the D matrices of all representations taken together with appropriate normalization factors is a complete orthonormal set in the space of square integrable functions on the group. This is true for all compact Lie groups. Okay.
This you don't have on the blackboard.
Which is not on the blackboard?
The completeness, you should be able to write something as delta A minus A, right?
Yeah, which is exactly what Mani asked a little while ago. What I am saying is that what he wants is contained in here. You take this, write this as an integral over the group. For this, substitute from the expression for the f's, put it all together in the mixer, run the mixer, shake it, out comes the completeness in the form you want it. Okay, and so this I leave as an exercise for you. I also want to leave as an exercise the following corollary of this completeness and relationship. Suppose you have, let me now switch to the Euler angle description. Suppose the function f that you are dealing with is constant over cosets with respect to SO2. That is, I have SO3, I take the subgroup SO2 of rotations around the z-axis. I take this subgroup, which we had a little while ago on the board, and I consider functions which are constant with respect over cosets with respect to this subgroup. In the Euler angle description, it means that the functions do not have any dependence on the right hand side exponential, on this angle phi. Okay, because varying phi, keeping these two factors constant, means you are just running over a coset with respect to SO2. And we are saying that a function is constant over such a coset. That means that functions over the coset space are just functions on the group which happen to be constant with respect to phi. If that were so, can you see some simplification in this expansion theorem? If the left hand side is known to be independent of the third Euler angle phi, the one at the right end, there is no phi dependence, what must happen on the right hand side? You know that the general D matrix has a theta dependence, psi dependence, phi dependence. This must not be present in this expansion for such functions. What does it tell you about the nature of this expansion? M2?
One of the M1 or M2 will not like it comes to be the constant.
So, which one? One of them. Which one?
M2.
M2. So, what do you say? What can you say about the nature of the M2 summation? You can't say it will not be there, but you must say something.
It will be there like a factor. Outside of this
No. Here, I will guide you to the answer. I could just tell you the answer, but I want you to. Here, this is a, what does this represent here? Three angles, theta, psi, and phi. And we are starting with the statement, there is no dependence on phi. So only such terms should be present on the right which have no dependence on phi. Correct? Phi terms with actual non-trivial phi dependence should not appear on the right. So what does it tell you about the M2 summation?
It will come one more 2 years plus 1 half x.
What is the, let me go back, this is so nice and important. What is the range of L? Range of values for the summation over L? 0 to infinity, all integers. For each L, what is the range of M1? All integers minus L to plus L. What is the range of M2? Plus L. All right. What is the phi dependence on the right hand side in a given term? E to the minus I M2 phi. Now I don't want to see this phi on the right. So what does it say? Only terms with M2 equal to 0 will survive. It will be exactly. So the way it works is that this expansion, which is available for every function on the rotation group, if you happen to have a function which is constant over each SO2 coset, it means in the Euler angle description there is no dependence on phi. It means in this expansion the only terms in M2 which survive the M2 equal to 0 terms. All right. So it means that for such functions, this is all that we need. We do not need all the matrix elements of all the irreducible representations, and M2 can be restricted to 0, and therefore I do not have it. I do not even indicate the variable phi. It's irrelevant. All right. So now I just leave it as an exercise for you to convince yourself. Such functions on the space of cosets or functions constant over cosets are really the same thing as functions on S2. We saw yesterday the coset space SO3 over SO2 is the sphere S2. Such functions are functions on S2. Such functions, for them a complete orthogonal basis is given by this subset of D matrices. What do you think these functions are? You know them. Spherical harmonics. It is just that the usual theta and phi, I have used different names for the angles. This becomes the polar angle, this becomes the azimuthal angle. So the statement that the spherical harmonics are a complete set for functions on the unit sphere is contained in this Peter-Weyl theorem for the full rotation group. You just restrict yourself to those functions on the group SO3 which are not dependent on the third Euler angle. Okay. I hope you find, you may know all these things already, but somebody somewhere wrote a nice line, there is always a pleasure in recognizing something you know from a new and comprehensive point of view. There is always a pleasure in recognizing the old. So this discussion about properties of the irreducible representations of SO3 has been from the point of view of solving the commutation relations, borrowing results from the quantum theory of angular momentum, and so on. There is, however, another approach to the irreducible representations of SO3, which is older, and it is there already in classical physics. It is called the method of Cartesian tensors. I will describe it very, very briefly. Now, the idea is quite elegant and geometrical. Take any matrix of the defining representation of the rotation group. You can, and it is useful to think of it as describing a change in the right-handed coordinate system in three-dimensional space around some fixed point as origin. So the transition from one orthogonal right-handed coordinate frame to another is described by a rotation matrix. So we can say, just to normalize our ideas, we can write each new unit vector as a linear combination of the old ones, and the matrix elements of A are just the direction cosines of the 3 old and the 3 new vectors with respect to one another. And of course, it is clear what are these equal to? The 3 old unit vectors by themselves or the 3 new ones by themselves, what are they? What are delta jk? These are both the Kronecker symbol. Now, suppose you took a 3-dimensional vector x. We would say that with respect to the original choice of axis, it has Cartesian components little x1, 2, and 3. The same vector with respect to the new Cartesian coordinate axis would have different Cartesian components. Put the two together and you will immediately see that the relation between the old and the new components of this 3-dimensional vector, they are given by the rotation matrix elements. So this is familiar to you. You know that a vector, yes?
In the first equation,
yeah.
Ej prime is probably having a kj.
I think this is correct. I think so. You can please check it. You may be right. In my notes, I have it in this way. Just double check this.
I later wrote xj prime.
Yeah. Maybe there is some error
One
here.
of them probably.
Yeah. Just check this. Huh? So shall we put a question mark here to please see. So this is a traditional pre-quantum mechanical way of describing what you mean by a vector in 3-dimensional space. A physical quantity is a vector in 3-dimensional space if in each coordinate system it is described by 3 numerical components, and when the coordinate system is changed, the components change according to a given rule. So a vector is a quantity which transforms in a particular way. Now this can be generalized to higher rank or higher order objects. We say that a Cartesian tensor of rank L is a collection of components written as T with many indices J1, J2 up to JL, where every index runs over the values 1, 2, and 3, such that when you make a coordinate system change, you rotate the coordinate axis, the old and the new components of T are related by this transformation law. So this is the definition of a Cartesian tensor of rank L. L can be any integer, 0, 1, 2, 3, and so on. Now, the fact that the same matrix A, the matrix which is real, orthogonal, and has unit determinant, the fact that the same A is appearing again and again on the right-hand side of this transformation rule tells you that among such tensors, there are 2 important invariant operations. The first operation is the following. You can take, here let me say, any 2 positions, position number R and position number S, with R less than S. You can set those 2 subscripts equal to one another and sum over them. giving them the values 1, 2, and 3. This is called the process of trace operation or contraction. When you carry out such a trace operation, you will get a Cartesian tensor of rank L minus 2, because what will happen is that the corresponding two matrices A will collapse because they are orthogonal matrices, and the contracted version of T prime will be related to the contracted version of T exactly in the same way, but of rank 2 less than T. So this means that from a Cartesian tensor of rank L, by pairwise contractions, you generate Cartesian tensors of lower dimension, from L to L minus 2 to L minus 4 and so on. Of course, if you carry out the contraction once, the result in general depends on the locations R and S which you trace over. If you were to sum over J1 equal to J2, you will get one result. If you were to sum J4 over J4 and J5, you will get another result. Both of them will be tensors of rank L minus 2, but they may not be the same. So this is one operation which is meaningful, which leads from tensors of a rank L to tensors of rank L minus 2, L minus 4, and so on. The other meaningful operation is the fact that it is the matrix elements of the same capital A which are occurring again and again. Therefore, suppose the original components had some special property with respect to permutations of these indices, you can be sure that the new components will continue to enjoy the same property. Whatever it was here, it will appear there also. In particular, suppose this was completely symmetric. It was symmetric under interchange of any pair of the indices. T prime will also have symmetry. All right. So this is very easy for you to appreciate. So now it turns out, suppose you take a Cartesian tensor of rank L. Let us say that it is symmetric, and let us also say that it is traceless. These would be the simplest Cartesian tensors that you can imagine. And it now happens that the number of independent components get drastically reduced. Let us see. Suppose you take a general tensor T of rank L. How many independent components does it have in each coordinate system? It has L indices, J1, J2 up to JL. Each index can take 3 values. So what is the number of components? 3 to the power L. Suppose you say, I don't want the most general, I want a symmetric T. In that case, I can ask you, how many independent components does it have? Every component is completely determined if you know how many of the j's have the value 1, how many j's have value 2. Doesn't matter where they are located. Once you know how many 1s there are and how many 2s there are, the balance will have to be 3s. This, does anyone immediately know the answer? How many independent components for a symmetric Cartesian tensor? It happens to be 1/2 L plus 1 into L plus 2. See the drastic reduction from an exponential type of dependence on L to a power law quadratic in L. Now you go one more step. You say, in addition to symmetry, let me assume it is traceless. That is, whenever I trace over any 2 pair of indices, the answer is 0. How many components do you think it has? Why will I sing this song unless the answer is something you expect? What do you think is the answer? How many independent components? Huh? 1. I can't hear you, sorry. I should have written here. What is this? What are these numbers? Number of independent components. That is what I am counting here. In general, 3 to the power L. Symmetric case, half L into L plus 1. Traceless symmetric,
Only one less than.
again I leave it as an exercise. It is exactly 2L plus 1. Please do this if you have not done it before. It is it is just a counting problem. And it is very nice. What does it tell you? It tells you that even without having to solve the commutation relations for the generators and going through the machinery of the quantum theory of angular momentum, here is a simple route to arrive at all the irreducible unitary representations of SO3. These are the representations carried by symmetric traceless Cartesian tensors of all possible ranks. This approach tells you directly why every irreducible representation of SO3 can be assumed to be real without any loss of generality, because nowhere have I introduced complex numbers. Cartesian tensors are perfectly well defined if we restrict ourselves to quantities with completely real components. Tracelessness, trace operation, symmetry permutation, none of these introduce complex quantities, and therefore this is a proof that they are in fact all can be made real. Okay? So as I say, this approach was known much earlier, and I don't know if some of you have heard of this beautiful book, Methods of Mathematical Physics by Jeffries and Jeffries. It's a very, very nice book. It is written in an old style, and I know that it is more than half a century old. But I also know that people like Chandrasekhar and Li and Yang learned their mathematical methods from that book. It's a very, very beautiful book. There I think you will find a description of Cartesian tensors. In that book, the emphasis is not on quantum mechanical ideas in any way. So this is just to show you this is already available in the classical literature. Go on to other things. Inclusion of parity. This leads to a group called the full orthogonal group. It is written as O3. And so let us begin with a defining representation for it. What are the conditions? A transpose. So this is the defining representation, the definition of the full rotation group. We do not put a condition that the determinant of A has to be plus 1. So it's called, it includes proper and improper elements. So clearly, if you look at the set of matrices which do have determinant plus 1, that would be what we have been studying up to now. And what are the others? They can be written as all those matrices in the group O3 which are of the form SO3 times the negative of the unit matrix. And now you see, because the dimension is odd, this is an improper rotation. It is, however, a multiple of the identity, so it neatly commutes with SO3. So I hope you appreciate that the inclusion of parity with the group SO3 formally is very much easier, very much simpler than it was with the case of O2 and SO2. So that is why I went through the discussion of the inclusion of parity for transformations in the plane in some detail, and you saw how much it affected the group properties of the group and also properties of the representations. So here things are much simpler. This part has determinant equal to +1. This is the part which has determinant equal to -1. So where is the identity element? First part. So it means that the manifold of the group O3, it is not a connected space. It is made up of two pieces. Each one is connected, but the two are disjoint. The piece which contains the identity is the SO3 subgroup, and that is usually called the identity component of O3. All improper rotations are in the other connected component, the one containing the parity transformation. So the nice thing is that the inversion operation, changing the sign of all three coordinates, commutes with all proper rotations. P commutes with SO3. For this reason, the unitary irreducible representations of O3 are very much simpler to describe and to list than it was in the case of 2 dimensions. What do? You have to just say it is some unitary irreducible representation of SO3 along with what? Well, the only other element which is non-trivial and which must be represented is the P operation, parity. What are the algebraic properties of P? P is not unity, but P squared is unity. So the only options are along with a value epsilon equal to plus or minus 1 for the element P. So this means that an irreducible unitary representation of the full rotation group is labeled by a pair of quantities, L, which is as usual quantized to have value 0, 1, 2, 3, and an epsilon which is either +1 or -1. So let me just tell you in full detail. For elements in the proper subgroup in this irreducible representation, it is just as before, as you had for SO3. And then for the other fellows, elements in the full group of the form parity times A, where A is a proper rotation, this is just epsilon d of A. So you decide what you want to choose for epsilon, and you get one representation or another. So let us look at simple examples. What would be the physical description of this representation of the full rotation group? 0, 1. L is equal to 0, epsilon is equal to +1. What's the physical word, the word for such physical quantities? What did you say? I can't hear. Somebody said something. I'm sorry, I couldn't hear. Those quantities which belong to this representation of the full rotation group are called scalars. What about those which belong to this representation? Pseudoscalars. What about 1, 1? Quantities with respect to O3 belonging to this representation. What is the name for them? Yeah, but vector by itself is inadequate. It does not indicate the parity behavior. So many words are used. Polar vector or true vector. Sorry, it is the other way around. Other way around. Polar vector, the components change sign under parity transformation. Axial vector, they don't. So tell me very quickly, example of this. Physical example in non-relativistic physics. Mass density. Okay. Example of this. Pardon? Volume. You are using differential geometry. I want a very simple-minded example. I allow you to use Newtonian mechanics and Maxwell's electromagnetic theory, just with this much geometry. Can you give me an example of a pseudoscalar quantity taken from these parts of physics? Electric field dot magnetic field, E dot B. That's a pseudoscalar. I want you to be aware of that. Give examples. Give me, how many shall I ask, Mani? 4 elementary physical examples of true vectors in mechanics and in electromagnetism. Please, in mechanics. True vectors. Come on. Position vectors of particles. Anything else? Momenta of particles. Anything else in electricity, magnetism? Electric vector. One more example from electromagnetism. Electric current. Space part. That's also a true vector. Examples of axial vectors in mechanics? Angular momentum. In electromagnetic theory? B. Okay? What is the Poynting vector? Is it true vector or polar vector? Why? Yeah, exactly. Very good, very good. So, Poynting vector is here, and magnetic field is here, and angular momentum of particles is also here. Okay, so this concludes my discussion of the three-dimensional rotation group with or without improper operations, and I hope that even for those who already knew something about this group, you have learned something additional from this description. There are many things which I have not proved. At least some of them, I hope you will make the attempt to fill in the gaps. I don't expect all statements to be proved, but at least some. I would be happy if you try. All right. Now comes a parallel account of the group SU2. And I do have some time, so I can go ahead. I can get started on this topic. Why do we have to study the group SU2? There are very good physical and mathematical reasons. This group is very closely related to the rotation group SO3. This fact was probably not very much realized in the days of classical physics. It has become clear and very important in the framework of quantum mechanics. It is also by itself important in so many physical applications, in classical polarization optics, in the description of the spin of elementary particles, half integer spin like electron, proton, neutron, and so on. In the quantum mechanical treatment of two-level atoms, two-mode radiation fields, in all these things, this is the fundamental group that is present. And also, for those of you who are interested in particle physics, many symmetries of elementary particle interactions are in the language of this group. What are the examples of the fundamental symmetries which use the group SU2? Isospin. Anything else? The electroweak unified theory. It is not the same as isospin, but it is SU2. One of the components is SU2. So this is enough justification to say that we should know what this group is. It also plays a crucial role in the quantum theory of angular momentum. So we must get a good hold of this group. So as usual, what we will do is to start with a defining representation. So what is the definition? from one point of view, it is actually easier than the three-dimensional rotation group, because the defining representation is in terms of 2 by 2 matrices. What could be simpler? The only thing is they are complex matrices. So that is where a lot of new structure comes. So once I had heard somebody, Goldberg, say that when anybody came with a fantastic new discovery he had made or she had made and wanted to tell Wigner about it, he would first check it for 2 by 2 matrices. If it didn't work, he would stop right there.
I just mentioned that in my class today.
You did?
The same state.
Same? And Wigner?
Yes.
Oh, I see. From whom did you hear it?
Well, I heard it from Wigner himself.
Wigner, oh boy, that's a real horse's mouth. I heard it second hand from Goldberger. Once when I first went to meet Professor Goldberger, I was sitting in his office, just introduced myself, and I had finished my degree and I had done some work on group representation. And who walked in to say hello to Goldberger? Bargmann. So Goldberger, he really had a joke at my expense. He introduced me to Bargmann and said he knows a little bit about group theory. And I, at that time, didn't know how much he knew. But over the next year or so, I learned a lot from his course. So this is the defining representation of the SU2 group, and the name is unitary. That is because of this condition. Unimodular. Unimodular means determinant equal to 1, group in 2 dimensions. That's the full description of this group. Unitary unimodular group in 2 dimensions. Now, in all the analysis that we will look at for this group, the properties of the Pauli matrices are extremely important, and I hope you are familiar with these. If not, just check the various results that I am going to write down. There are, yeah? Somebody said something? These are the 3 Pauli matrices, and what are their most important properties? They are Hermitian, traceless, and if you multiply any 2 of them, the result is like this, and trace sigma j sigma k is 2 times delta jk. These are the most important properties of the Pauli matrices. So there is a very simple mnemonic which one often uses. If you take 2 numerical vectors a and b and you construct this product a dot sigma, b dot sigma. So these are 2 by 2 matrices. And if a and b are real, these are Hermitian matrices. This is a1 sigma 1 plus a2 sigma 2 plus a3 sigma 3 and so on. So what is this equal to? A dot b plus I sigma dot a cross b. All right. Always it is understood that this so-called scalar term is multiplied by the unit 2 by 2 matrix. I don't write it explicitly. Okay. So these are very important rules of calculation. So next what we will do is look at 4 interesting ways of describing the elements of this group. And I go through all of them because I have told you in how many contexts this group plays a role. So it is important for you to feel really familiar with the elements of this group. We will see now 4 ways of parameterizing elements of this group. 3 of them are extensions of what we have already done for SO3. They are extensions, they are not identical. The fourth one is specifically for SU2. So let me write them, A, B, C, D. I want you to prove the following. A matrix of the defining representation of SU2 can always be written uniquely in the following way. In terms of two complex numbers, alpha and beta, obeying the condition mod alpha plus mod alpha squared plus mod beta squared equal to 1. So I want you to prove that that is the most general solution to these two conditions on the matrix U. Unitarity condition, determinant equal to 1 condition. So you must do this. If you do not know this earlier, you must convince yourself that this is a way to describe every element of SU2. So now, can you immediately guess what is the manifold structure of SU2? Huh? S3. How do you see that?
The square is 2 alpha square plus alpha.
Pardon?
Suppose if you write alpha is equal to alpha 1 plus I alpha.
Yeah.
Beta is beta 1 plus I alpha. So it will be alpha also plus alpha.
Correct. Sum of the four squares of the four real components has to be 1. So this immediately tells you that SU2, the full group, has the structure of S3. Right? And it was this which I think Simon told me one day. There was a 2-hour discussion to check this fact somewhere here. You told me once. So you can see that the group SU2 can be pictured as 1-to-1. Its elements correspond to points on the surface of the unit sphere S3 in 4-dimensional real Euclidean space. But remember, we also have a picture for SO3 in that space. What is it? It is S3 or something else? S3 with a rule of identification. What is the rule of identification? Huh? Diametrically opposite points have to be thought of as the same. So here is a hint that SU2 is twice the size of SO3. We will see that in full detail later on. The next 3 descriptions are generalizations of the SO3 descriptions, and I give them in such a way that they match very nicely. This axis angle description says any matrix in the defining representation of SU2 can be uniquely written in the form which I am writing now. Not uniquely, almost everywhere. Every element of SU2 can be thought of as specified by an axis n and an angle alpha. N can be anywhere on the unit sphere S2, the familiar S2. The angle alpha can go all the way from 0 up to 2 pi. And if you combine the n and the alpha into a 3-dimensional single real vector, this can also be written in that form. Cosine alpha by 2 times unit matrix, of course, minus I alpha dot sigma over modulus of the alpha sine alpha by 2. So this is the axis angle description. Just a matter of notation, this angle alpha in this description, please don't confuse it with the complex alpha in the first description. This is standard notation, so everybody uses it. So you just make sure this alpha and that are not the same. Of course, one can ask, this complex alpha, what is it in terms of axis and angle? You can work it out. You can write down this 2 by 2 matrix here and here and read off the 1, 1 element. That will be alpha. Similarly, you can get beta for this description. So this is the second description. Third one, homogeneous Euler parameters. It is a fact. So these are all things which you must verify. Any SU2 matrix is uniquely expressible in this form in terms of a unit vector in 4-dimensional real Euclidean space. So this is called the homogeneous Euler parameter description of SU2 elements. How do you connect up this description with the axis angle? What is A0 and what is A? Just to make sure that you are comfortable. What is little A0 in terms of axis and in terms of alpha vector? What is A0?
2 times real part of alpha.
No, in terms of this one. Not this one, this one. Cosine alpha by 2. And the 3 vector A,
Sine alpha by 2 n vector.
let us say, put it in terms of correct? So this is how the two are connected. See once again, as we saw in this alpha beta description, elements of SU2 correspond 1 to 1 to points on the sphere S3. Does this already show you something about the connectivity of SU2? If you can imagine the unit sphere in 4 dimensions, and if you imagine putting a loop on it, don't you think it can be slipped to the north pole and pulled out? So it is simply connected. And it is so because distinct elements, distinct points on S3 denote distinct elements of SU2. There is no identification that this point and the opposite point should be thought of as the same. That is not there, and that is what makes for a topological difference between SU2 and SO3. And the last one, shall I finish it and then I can stop? I can sleep more easily. The Euler angle description. This is the fourth one. Just a little bit of background. What we have to remember is there is a relation which can be written in this axis angle description, which is the analog of what we had for the rotation group, relating rotations about a given axis and rotations about the opposite axis. So this is the, sorry, which way have I written? Yeah, this is correct. I had to interchange the two. And it is for this reason, notice the appearance of 4 pi, not 2 pi. It is for this reason that here it was enough to allow alpha to go up to 2 pi and not beyond. Because allowing alpha to exceed 2 pi can be accomplished by switching the sign of the axis. Okay, so now here is what is called a U1 subgroup. I have not introduced or defined the U1 group at all, but it is a group of all complex phase factors of modulus unity, and I think you all know what it is. So if you take all SU2 elements with a fixed axis, and you allow alpha to go up to 4 pi, they form a subgroup of SU2. And I will use the notation U1 to tell you what subgroup it is, and N to tell you which axis it is. So what does it mean? You take all these 2 by 2 matrices, keep N always fixed, but allow alpha to take all possible values, not only up to 2 pi, but up to 4 pi. Then you will get a full subgroup. This is called the U1 subgroup with N as axis. And as you vary N, you get different U1 subgroups. It is exactly analogous to thinking of two-dimensional rotations in various planes as subgroups of three-dimensional rotations. So with this idea, one can convince oneself. This involves a little bit of algebra. First, I would like you to do the following. Look at the general definition of U of n and alpha, which I just rubbed out. Axis n and angle alpha. And take for n the unit vector in the direction 1. And the element of angle alpha, how much is this? It's a 2 by 2 matrix. Please tell me what is the structure of this matrix. What's the 1, 1 element? You understand what I'm? Huh? Cos alpha by 2. I'll just write C. C stands for cos alpha by 2. S stands for sin alpha by 2. So what is the 1, 2 element? Minus is. This one? Yeah, can you tell me immediately from that first description, the alpha beta complex description, from there itself you can see this has to be this. And what does this have to be? Star of that. So it has to be C. What is this? Yeah? Yeah? Yeah. Yeah. Very good. And what is the third one?
Exponent of minus S.
Huh?
No, exponent of minus alpha by 2.
Minus?
Alpha by 2.
No. I.
I alpha, sorry. I alpha by 2.
Yeah?
And 0, 0, e to the power alpha by 2.
Yeah, exactly. I alpha by 2. And in all these subgroups, it has to be understood the range of alpha is up to 4 pi. Okay? So these are the 3 of the infinitely many U1 subgroups in SU2. I want you to appreciate any axis in 3-dimensional space, that's a corresponding U1 subgroup of SU2. If you take n axis n to be along the direction of the x-axis, you get E1. Y-axis E2, z-axis E3. So here are some very elementary formulae which I want you to verify. Each of these can be written in exponential form involving the rotation angle alpha and the appropriate Pauli matrix. And why do we expect such an alpha dependence? It is because suppose you take this element in this subgroup with angle alpha and you take the same subgroup element with angle beta and you compose the two. What should happen? The angles should add, which is why it should come up in the exponential in this way. And you can immediately generalize this in the axis angle description. Every element of SU2 can be written in exponential form in that manner. So we say that the Pauli matrices with a factor of half are the generators of the defining representation of this group. And now it is a matter of simple algebra, but you have to be a little careful that every element of SU2 in the defining representation is uniquely, not, sorry, is almost uniquely, not quite, expressible as a product of three elementary exponentials. Which means what? That it is a product E3 theta U E2 psi U E3 phi. This you must check, and you must find out for yourself the complex alpha beta description, the first description. What are alpha and beta in terms of these angles? Work it out and make sure you see that mod alpha squared plus mod beta squared is equal to 1. And the important thing is to see what are the ranges, and I just take a convenient set for the second and third Euler angles. The ranges are the same as in the case of the rotation group SO3. For the first angle theta, you have to allow twice the range. You have to allow alpha theta to go all the way up to 4 pi. Unless you do that, you will not cover the entire group SU2. So this is the Euler angle description of SU2. It is the analog of what we had for the rotation group. And once again you see this group is double the size of the older group SO3, because for one of the three angles the range has got doubled. The other two, no change. Okay. If all of them had got doubled, you would have to say this is 8 times as big, but that's not true. It is only twice as big. Okay. So I stop at this point. I have done a good amount of SU2 introduction. If you have the time tonight or tomorrow, just familiarize yourself with the defining representation, properties of these 2 by 2 matrices, how we exploit the Pauli matrices, and these different equivalent ways of describing its elements. The Euler angle thing, it is not a globally well-defined coordinate system. It is not true that there is a unique set of Euler angles for every group element. For almost all group elements, the Euler angles are unique and well defined. For certain ones, a set of measure 0 as it is called, these things are not uniquely determined. You can easily see when if psi were 0, only the sum of theta and phi is relevant. With the other, the homogeneous Euler parameters and so on, things are neater. Okay. Okay, so we'll stop at this point. Yes, please.